everybody, welcome back. Here's my next video. I'm going to talk about series and parallel circuits. So basically what we're going to do is take it a step further from the Intro to Circuits PowerPoint slide, and what I'm going to do is add more parts to our circuits. But more importantly, the way you connect them actually changes the whole circuit, how it behaves, how the current changes, how the voltage gets distributed to each of the devices. So all this changes when you connect them differently. And there's two main types of connections that happen. There's one that's called series circuit, and there's one that's called parallel circuit. So I think they look, noticeably different, but we'll talk about the circuit connections. And this all applies to conservation of energy and conservation of charge. So I'll talk about those conservation laws as it involves these circuits. Lastly, what I'll do is I'll do it as a separate video, but what I'll do is I'll actually solve these circuits completely. In other words, I'll solve for each of the current, the voltage, and the resistance equivalents for each of the circuits. Okay, so I kind of talked about all this right here, so I'm going to move on here. So we're going to start off with what is called a circuit, a series circuit. So what a series circuit is a connection at which all of the resistors are in a single loop. So if we were if the whole class were resistors, okay, and we wanted to make a series circuit, we would each get into a big circle where we're all holding one other person's hand. So we're making a giant loop with that. So what happens is, since there's only one loop, there's only one way for the electrons to flow. Therefore, the current across any one of these devices is the same. So in other words, if the current through the battery is 2 amps, the current through this resistor is also 2 amps. In other words, we won't have a case where the battery has a current of 5 amps and the resistor has a current of 3 amps. The only way that could happen is if there's another path for these electrons to go through. And if you think about it, it would be like if the electrons were going like this and then speeding up and then slowing down. So same thing. If you think about a river, the only way the river is going to change its speed in any one location if the river breaks off. So kind of similar concept here. What happens though is, because the electrons are carriers of energy, and they have 3 stops in this case to go to 1, 2, and 3 resistors, they have to share that energy. So I put the voltage adds, but I like to say actually that the voltage splits. And what do I mean by that? Let me see if I just wanted to see if I had something there. So what happens is, if I have 10 volts of energy to give to my circuit, then I would have to split the 10 volts amongst these 3 resistors. Now, how I split them depends on their value, but if they're all the same, then they are split evenly. In fact, I actually want to show you this, just to be very specific about this. There we go. Let's go ahead and do this. And I'm going to make a series circuit, but I'm going to do it with light bulbs just because you can see the brightness. Of course, you could do this with resistors as well. That's totally fine. So here's our battery coming in. So try to make it look like my diagram on purpose. 2, 3. There we go. And I'm going to crank up the voltage just so it's a little bigger. And in fact, I'm going to do it specifically to a nice number. Let's do 36. Okay. So I hope you notice that in this circuit, you can see that the electrons are all moving at the same speed. That if I were to take this ammeter right here and put it right there, you would see a current of 1.2 amps. And that if I put this somewhere else, say right here, it will be a boring 1.2 amps. So the current is the same through each one of the branches, and through the bulbs, and through the battery. So the current is the same in series. But let's take a look at the voltage. So right now I have 36 volts that the battery can provide to each of these bulbs. if I measure the voltage, you'll see that I have 12 here, 12 here, and 12 here. Ignore the negative sign, but 12 times 12 times 12 is 36. So you can see how the voltage is split. Now, since they're the same, they have the same voltage. But if I were to change this, for example, let's make it 20 ohms, like that, we would find that these are different. This now becomes 9, 18, and 9. 9 and 9 is 18, and 18 and 18 is 36. So once again, the voltage splits up when it's divided up like that. Excuse me one second. Just want to check one thing here. Okay. All right. So that's what I mean by the current splits up. And I'm going to change this back to, okay, 10. There we go. Move that out of the way. We're going to use this again, like that. So I like to say this circuit likes to share its energy. As you can see, it splits it up. And they usually become dimmer because the circuit shares its energy. So here's an animation. I kind of like it because it kind of shows you a three-dimensional way to think about energy. So once again, remember that, that the charges are being energized here. That's why it's on this escalator. It's giving potential energy. So kind of think of it that way. Now we always model the motion of positive charges, so that's why they're positive, not negative. And then you could see the 30 ohm resistor takes more energy than the 10 ohm resistor. But then we're looking all the way back down, and then we get re-energized again. The circuit has the same current throughout. We're conserving energy, by the way, coming back to my topic right here. If we start off with, for example, 36 volts, we end with 36 volts. So we're conserving energy. And technically charge, because the number of charges don't change here. Charge is not added or removed during the circuit at any point. Another interesting feature is this thing called the resistance equivalence, or the total resistance. Now the battery right here doesn't know if there's 3 resistors here, or 1, or 40, but it knows, it could feel it in terms of current. So instead of taking these 3 and doing them separately, I can kind of take those 3 and squish them together into what we call resistance equivalence. So what I'm going to do is combine these 3 resistors into one. And the way you do that, luckily, is for a series, you just add them up, which is kind of nice. So if you have 6 and 6 in series, it's the same as 1 12 ohm. And this is the same as 1 18 ohm. And this is the same as 1 24 ohm resistor. Hope you get the point. It's kind of nice. I love series because you just add them up. It's very simple. So of course, let's do an example of this exactly. I just want to see where we're going here. So there you have it. So if I want to find the resistance equivalence of this circuit, there we go. REQ is going to be 17 ohms. By the way, just backtracking, REQ is the sum of these. So I'm going to take the sum of the 3 of them. And this works out to a really nice number of 40 ohms. So the REQ, so this circuit is the same as a circuit with 60 volts and 40 ohms. These two are equivalent, hence the word resistance equivalence. So now we're going to go into a different type of connection called a parallel circuit. Now with parallel circuits, the connection's different. If I use the same example, if all of us in the classroom were resistors, in order to make a parallel connection, we would all have to hold, all of our left hands will be holding the same spot, and all of our right hands will be holding the same spot. It's a weird connection. And in fact, I don't think all 30 of us could actually make the connection physically. But that's how we would make it. And I hope you notice that this is visibly different. one of the major features of a parallel circuit is the fact that there are multiple paths for the electrons to go in. I call these branches. That the electron comes to what this is called a junction. It's kind of like going to a stoplight, right? And you have a choice to go, in this case, straight or left. It's kind of the same thing. If you think about when you drive in your car and you come to that stop sign, you can't be in two places at once. Either go left and go down the street, or you go straight and go down the street. So the current splits here. So unlike series circuits and parallel circuits, your currents actually split. But just like series circuits, they conserve their charge. So in other words, I'm just going to make up the numbers for the sake of making up numbers. But say I have 10 amps coming in right here. At this junction, some of the current is going to go here and here. And I'm just going to make up numbers because I actually don't know. I'd actually have to calculate it. But to make the numbers easy, it would be, for example, like 2 amps might go down here. So to conserve charge, then 8 would have to go down here. And then you would come to this junction, and maybe 3 goes down here, and then the rest of the 5 go down here. Or in other words, if you notice, 2 plus 3 plus 5 make 10, where you have this little branch that's slightly different. But if you follow this down, the 5 will meet up with the 3, and this will meet up to make 8. 3 plus 5 will come out to 8, and then the 2 will meet up, so this will come back to 10 amps. So that's the biggest difference. That's why I say in a parallel circuits, the current adds up. Now, because I'm an electron giving my energy, in this particular case, I only have one house to go down. So that means I get to give all of my energy. So when I get here, I release 9 volts. Remember, I can only go in one spot. So if I go down this path, I'll release 9 volts. But if I go down this path, I'll also do 9 volts, etc. So in this case, the energy given is the same. But what happens is the current splits, and we conserve charge. Because the number of charges that go down here don't disappear, and are not created. So think of it that way too. So that's what I mean. So the current in the battery is going to equal to the sum of the branches. So just like what I said here, so the current in the battery in this case was 10 amps, and the branches was 2, 3, and 5. Now, because the current splits and you get all of the energy, they're generally brighter. And another feature that I didn't actually talk about with the series circuit is if one of these bulbs goes out, say this one breaks, well, the electrons don't need to go down that path. The circuit still works because it can go down a different path, unlike our series circuit, right? If this bulb were to suddenly go out, the whole circuit doesn't work. So I don't know if you ever heard that Christmas song, but they say, if one goes out, they all go out. That's true for series circuits. But for parallel, that's not the case. So I'd like to show you an example anyway, even though I kind of did one there. I'm going to show you a circuit connection here. And it's very important that I do it exactly the way that drawing is, because otherwise the simulation won't work. So I'll put one branch here, put one here, it's a all wonky, that's okay, and one here. So I'm going to just divide this up into 1, 2, 3 parts, where I'm going to add my bulbs. And my wires. Okay. So if you take a look here, first of all, they're definitely noticeably brighter than what we did before. But look at the current. look how different it is, right? Look how much faster it is through the battery than it is through the branch. And even this part of it, look, it goes super fast, slow, slowest, right? So we can measure that. So I'm going to take this one out and get the current through the battery. So about 10 amps here. Oh, I can do this. This is exciting. Here's the current through this branch, 7.2. And then the current through here. So notice the difference, right? The battery is much faster, 10 amps. This little branch right here, 7 amps. And then this branch right here, 3 amps. But if you notice, if I did 7.2 plus 3.6, I would get 10.8. It works out. In fact, I can even do this, put this wire back in, and then put the ammeter here, but it simulates the very similar case that we kind of looked at already, the 3.6. In fact, if I were to put the ammeter in all three of the branches, you would see that they're the same because I have them as the same resistances right now. And there you have it. So they're all the same. So 3.6 times 3 will give us 10.8. So, like I said, if I took out one of the bulbs, the circuit certainly changes, but it still works. And the interesting thing is, notice how it decreased over here, right? That's because the battery doesn't need to work as hard because one device is missing right here. Okay, and then like I said, the voltage, let's take a look at the voltage. So the voltage for each. So I have 36 volts here, 36 here, and 36 here. There we go. So the voltage stays the same. The current in the branch is split. And in this case, you can visibly see the current being different, being fastest through the battery, and then slows down as it goes through the circuit. And I hope that makes sense. The battery has to work extra hard when you put more and more branches here. This is what happens in your household. Your household works this way. It's actually all connected in parallel. Because if you think about it, it would stink if the whole house went out if you took out one light bulb, right? If you shut your lights off in one part of the house, the whole house goes out. Watch what happens when I add another branch. I want you to see this. So look at the current right here. Notice I got more, right? This is what happens when you have your hair dryer in, the vacuum going, the washing machine, the dryer. If you have too many things in the same circuit, you actually overload the battery, and that's where that fuse comes in, right? So the fuse is actually in series right here. In fact, this is definitely going to go out because this fuse is only rated for, right now it's rated for 20 amps. But if it goes under, our current right now is what, 14? Boom. This is you blowing a fuse. And this is how your house is pretty much wired for the most part. Pretty interesting stuff. All right, so we did everything here. If you look at the difference here, you can see that the energy changes is different than the series, in that both the resistors have the same drop in energy, right? You can see that. And then, of course, if you look at any one part of the circuit, you can see more current through the battery than you do through each of the branches like this. We can do the same thing with parallel circuits, but in order to model it correctly, the mathematics is different. In fact, we get this 1/, factor. But when I solve resistance equivalence, I like to use this method instead because I actually find it easier than using this one. Because when you solve this, the biggest common mistake students have is they leave it as 1/REQ. In other words, they'll solve this part but not finish off by taking the inverse of that. So let me show you this calculation right here, because it is a tricky one. So if I were to do this with this equation, so it'd be 1 over REQ equals 1 over 6 plus 1 over 6 plus 1 over 6. And I'm going to do that in my calculator. 1 over 6 gives me, move this over. So if I do this out, it gives me 0.167 plus 0.167 plus 0.167. I just did the three of them, right? So I get 1 over REQ is equal to 0.5. Now, like I said, a lot of people make this mistake and stop here. But the problem is we're solving for REQ. Which means I have to get it out of the bottom. So I have to take the inverse of both sides to do that. So if I do 0.1 over 0.5, so REQ is going to equal to 1 over 0.5. I have to do that last step. And that's where the 2 ohms comes from. Now, I like to do it this way on my calculator. So I do 1 REQ to the -1, and I do 6 to the -1. So I actually have a -1 on my calculator here. I hope you could sort of see it. There it is. Right in the middle right there to the -1. And this way I don't have to worry about fractions. I think that's the biggest thing. 6 to -1 plus 6 -1 plus 6 -1. So much faster. REQ equals 0.5. I get the same thing. But what I'm going to do now is I'm going to take that answer and just, I don't know if you can see this. Let's see. Answer to the -1, right? And that gives me 2. So basically I do REQ is equal to 0.5, and I use the -1 button on my calculator, and that gives me 2. So in a parallel circuit, you reduce the resistance whereas in series, you add resistance. Okay. So I have the same kind of example here. So I'm going to do it like this. REQ to -1 is going to equal 17 to -1 plus 12 to -1 plus 11 to -1. 17, oops, -1 plus 12, -1 plus 11, -1. So I get REQ equal to 0.233, but I have to take this whole thing to the -1 and this whole thing to the -1. So then I get REQ is equal to 4.29 ohms. And there you have it. This is a tricky calculation. I recommend you definitely try these out and see if you can get these answers. And if you can't, please reach out to me so I can help you through them, because I know people have trouble with the inverse fractions. Okay. Ooh, these are fun. Combo circuits. So how do you solve something like this? Well, the way you got to do it is you kind of have to start from the inside and work your way out. So you're going to take those, for example, we're going to take the parallel. See how there's a parallel within a series? We're going to start by squishing the parallel first and then rewriting it into a series. So I'll show you. So for this case, what I'm going to do is take these two and isolate it and pretend that this is the only one that I'm worrying about. So the REQ for this, since it's in parallel, will be 4 -1 plus 12 -1. Which gives me REQ, -1 equals 0.333. Remember, I got to do that last step and take the inverse again. And the REQ here is 3. So in other words, I have a 2 ohm resistor, which I just basically took here and dropped it down. And then I squished this down into a 3 ohm resistor. Now, this is in series. And I love series because I just add the two together. So the final answer for this combo circuit is that this is a 5 ohm resistance equivalence. So this would be the point where I say you try, and you would try this one. So why don't you try it? Pause the camera, or not the camera, but the video, and give it a shot and see how you do. Okay, so the way to do this one is you leave these two alone, and you find the REQ of this. Of course, I'm solving this pretty fast, but what I get here is 2. So these 3 resistors squish down to 2, and this is in series, so I just add these up. So 1 plus 3 is 4, plus 2 is 6 ohms. And this is the REQ of this combo circuit. I think for extra credit on the next quiz, you'll probably have a combo, a tricky combo one, not like you'll have one of these as a multiple choice, but not like a crazy one. I won't go anything more complicated than anything that you see here with that. Great multiple choice question. How does the brightness change? So if I added another bulb here, I would have to split more energy. So like that's like if you had like a cookie, and when you had 2 people, you broke it in half. But now you added a third person. Instead of breaking it in halves, you have to break it in thirds. So this would actually decrease brightness, because we certainly will have less voltage between the bulbs. What about this? If I add another place for the electrons to go, I get the same energy. I do split the current, so it's a little less, but overall I get the same voltage here. So I would see relatively the same brightness, same-ish. I put same-ish only because it doesn't change the current by that much. I'm assuming that this is the same value. So this, if we added another bulb to this circuit, it would still remain relatively the same brightness because you're getting the same amount of voltage. And the current now splits into thirds. So, I mean, it's a little less dim, but not by much. How does the brightness change if one of them goes out? Okay, so if this goes out, they all go out. So it's no longer lighting. So you could even say dim. If one goes out, the brightness stays the same, because you get relatively the same voltage and relatively the same current. So these will actually stay the same. I say relatively the same because the current will actually decrease ever so slightly, but not by much. In fact, you would notice a change in the brightness. So think of your house, right? When you turn off a light in the house, not all of the other lights go dimmer. So that's kind of the same idea here. So you do this in your lab too, but this is a fun activity. This is something we do in the class, so usually I'll just do that. But for now, let's pretend you thought about this. What would be the highest brightness? Would it be A, B, C, or D? And then explain the ranking, assuming each of the bulbs are the same amount. So let's say that we took a break and we thought about this. The final answer is the following. with the greatest brightness, it's going to be A, then D, and then B and C are equivalent with the lowest. Now the reason why is because you get the most current near the battery. Because what happens when you get to the junctions is the current splits, right? So both of these will inherently have less current than here. I is greater than those two. Just as an example, if this was 5, this might be 2, and this might be 3. So first of all, you get more current here. And notice that this bulb doesn't have to share with other bulbs too. So this gets a lot of current and a lot of voltage. Although the focus of this is not calculating the brightness of the light bulb, it can be calculated by IV. So the more I and the more V, the brighter it is. This is called power. Now notice the next one is this one, mostly because, not so much numerically, but if you look, that B and C would have to share their voltage here because they're in series, even though they're in parallel with this. In fact, the combination of the two would equal 3, and this equals 3. So it would lower the current because the two resistors would add up, increasing the resistance down here. And have less voltage. So this thing will also have just less current, less voltage. So that's why they're the least. Now they're the same because we assume they're the same bulbs, so they will have the same voltage and current. It has the same current because it's in the same branch, and additively, it would have the same voltage. And then the reason why D is second is because it doesn't have to share its voltage, but it certainly has less current than A, because A is getting the full current, where this is getting the split of the current. So that is something you might see on the quiz, because this is of course, this is a challenging question, but it really tests your knowledge of parallel and series circuits. So same thing, rank the bulbs in terms of brightness. Definitely take a stab at this first before I do it. But it would be total power produced by the battery. It would be this C, A, and B cab. Now the reason why is because when you put things in parallel, you reduce the resistance, which means automatically I is going to be higher in a parallel. Now, this one, if you put them in series, this is going to increase resistance, which means it's going to reduce current. And then comparatively, this is in the middle because we're not reducing, or the resistance is not, how should I say? This lowers resistance, this increases resistance, this decreases resistance, so that puts this in the middle. So that would be the order of this one right here. All right. So as you can see, the biggest thing about series and parallel circuits are the following. That in series circuits, the current is the same, but the voltage split. If one goes out, they all go out, and they're mostly dimmer because of the splitting of the voltage. And as you add more to the circuit, you're increasing the resistance, therefore reducing the current. So it gets dimmer and dimmer each time you add a light bulb or a resistor. In comparison to your parallel circuit reduces resistance, therefore increases current. The current splits across the wires, but keeps the same voltage, which is why they're usually brighter. And if one goes out, they still work. Okay, so I'm going to end this video right here, but what I'm going to do in the next video is, what I'll do is called solve these two circuits. I'm going to solve for the current and the voltage across each one of those devices. I'm going to use both concepts of parallel and series circuits as well as Ohm's law to solve this out. I'll see you in the next video.